when we're doing titrations, and it can be a bit confusing, is we really need to break it down into two steps when we're doing a titration. First off, whenever we do a titration, we have to standardize the solution that we're going to use to titrate our unknown. So we perform a titration with a known amount of a standard chemical, otherwise known as a standard. And then we calculate the molarity of that titration solution because we know how much we put in there. Then we go and perform the titration on the unknown solution with our standardized solution. Usually we put an indicator in there so we can see when the endpoint has been reached. And then we calculate the molarity of the unknown solution, and if we know how many grams of the unknown we have, we can actually calculate a molecular weight. Then we move on to a problem, and this is my example problem, and we're going to standardize a sodium hydroxide solution first, and then we're going to titrate an unknown acid to determine the molecular weight and also the molarity. So part one, we've got 5.678 grams of KHP, which is potassium hydrogen phthalate, and we dissolve it in some water to make up a solution. If we know the number of grams of KHP and we know the volume of our volumetric flask very accurately, then we're going to be able to calculate a molarity off of that. And then we pull out some of that, 25.06 milliliters of this, and we put it into a flask. And it doesn't matter that it's a 250 milliliter Erlenmeyer flask. It just needs to be big enough to hold what we're putting in there. Put some indicator in there and we titrate it, and it takes 26.64 milliliters of our sodium hydroxide solution. Now, the sodium hydroxide solution is an unknown molarity. We're using the known molarity that we're going to calculate of the KHP to calculate the sodium hydroxide solution molarity. Then we'll use that known molarity for the sodium hydroxide solution to titrate our unknown monoprotic acid in part 2. And then once we determined the equivalency point, then the number of moles of sodium hydroxide will be equal to the number of moles of known molarity standard acid. And then we can calculate the molarity and molecular weight of the unknown acid. So we're going to follow a procedure, and I'm going to lay it out to you step by step so you can see for yourself. So let's go ahead and calculate the molarity of our standard sodium hydroxide solution. So what we're going to do is we're going to weigh out a portion of a known acid and a standard at that. This is potassium hydrogen phthalate, and we're going to dissolve it in a precise amount of water in a volumetric flask, and we're going to get a molarity out of that. And then we're going to pull some of this out into another Erlenmeyer, and then we'll titrate it. Now, when we pull this amount out, this is a specific number of moles, the milliliters, and we have the molarity we're going to calculate up here. And so the number of moles we put in this Erlenmeyer flask is going to be equal to the number of moles of sodium hydroxide solution that we titrate in. So first off, we need to calculate the molarity of our standard acid KHP, and KHP is potassium hydrogen phthalate. And it has a molecular weight equal to 204.22 grams per mole. Okay, now we got 5.678 grams of this, and we want the molarity of the solution. So why don't we go ahead and get the number of moles first. And it's 5.678 grams of KHP. And we know that 1 mole of this is 204.22 grams, and that gives us 0.0278033 moles KHP. 250 milliliters is 0.250 liters. If you recall, we want the molarity, and molarity is in moles per liter. So to get our molarity of KHP, that's going to be 0.0278033 moles divided by 0.250 liters. Recall, 2.250 liters is 250 milliliters, and that gives us a molarity of 0.111213 molarity kHp. Now we need to know the number of moles that we're putting into this new Erlenmeyer flask there, because however many moles we put in this Erlenmeyer flask is what's going to be neutralized by the sodium hydroxide, and that will tell us the number of moles of sodium hydroxide. So we had 25.06 milliliters of this solution. So let's just go ahead and multiply times 25.06 milliliters. And this is moles per liter. And what this will tell us, now I know we're not canceling units here, but this will give us in millimolars. This is milliliters. Liters will cancel and we'll be left with millis. So this will be millimoles of KHP that went into that 250 milliliter Erlenmeyer flask to be titrated. And this gives us 2.78701 millimoles of KHP. Okay, now that's the number of millimoles of KHP. So what that tells us is that the equivalency, since the moles of KHP that react with the moles of sodium hydroxide is 1-to-1 by stoichiometry, that whatever, when we reach the equivalence point, this will also be the number of millimoles of KHP. And we can go ahead and just say that. That's also the millimoles of sodium hydroxide. We had 26.64 milliliters of this, and since this is millimoles, we can say, well, the molarity of the sodium hydroxide is now this, which is the millimoles, divided by the number of milliliters, and that gets rid of our milli. So we've got 2.78701 millimole of sodium hydroxide, and if we were to divide that by the number of milliliters, and that would be 26.64 milliliters sodium hydroxide. Millis cancel and we're left with moles per liter. Millis cancel and we're left with moles per liter, and that gives us the molarity of our sodium hydroxide, and that gives us our standardized solution of sodium hydroxide. So to recap, we know the molarity of the KHP in our 250 milliliters, and since we know how much we took out to put in our 250 milliliter Erlenmeyer flask to titrate, then the number of moles of sodium hydroxide that we titrated into that solution is exactly equal to the number of millimoles in that portion that we took out. And there you go right there. And there's our standardized solution for the sodium hydroxide for part 2. In part 2, we're going to take our newly standardized sodium hydroxide solution, and we're going to use that to titrate an unknown monoprotic acid. Okay, now it's important that that we know that it's a monoprotic acid, because that enables us to use a 1-to-1 mole ratio between the standardized sodium hydroxide, which produces 1 OH per mole, and with the unknown monoprotic acid, which produces 1 H plus per mole. So being monoprotic allows us to make a 1-to-1 mole ratio, which means however many moles of standardized hydroxide solution that we use for the titration is going to be exactly equal to the number of moles of monoprotic acid, which is dissolved in a 250 milliliters volumetric flask. And we use that moles to calculate the molarity and the molecular weight of the unknown acid, since we'll have moles per gram, which would be the molecular weight. So we don't worry about this until the very end. We actually calculate the moles of standardized sodium hydroxide solution that we used. And so it's 58.29 milliliters of sodium hydroxide times our standardized molarity, which we just figured out from part 1, big M. And if we multiply the milliliters times the moles per liter, we get an answer in millimoles, which is convenient to use, 0.069814 millimoles of sodium hydroxide. That's the number of moles that we used in millimoles to titrate that unknown. And now it's really easy to figure out what the molarity of that solution is. Like, for instance, if that was a hydrochloric acid solution and we want to know what the molarity of that is, well, it's real easy. We've got the moles, we've got the volume, which is 250 milliliters. We didn't take out any, we left it in there. And so that's 6.09814 millimoles of the acid. Remember, it's 1-to-1, so however many millimoles of sodium hydroxide we use for titration is exactly equal to the millimoles of the unknown acid, and that's per volume, which was 250 milliliters. That's the millimoles in the original. Now you got to keep them straight, because this is the milliliters of the sodium hydroxide titration. This is the milliliters of the acid that was in that solution to begin with. And that gives us a 0.02439 molarity of the unknown acid. Okay, just to show you that you can do that. But now we need to go ahead and figure out, well, what's the molecular weight of this unknown acid, which is usually what you're asked in these sort of experiments. Well, first off, we need to convert that from millimoles to sodium hydroxide, because our molecular weight's going to be moles per gram, not millimoles per gram. Okay, so let's go ahead and take that to just moles, millimoles of the acid. And you'll recall that there are 1,000 millimoles in a mole, and so 1 mole is 1,000 millimoles, and that gives us 0.0060984. I'm not using scientific notation because I don't really need to. And that's moles of the unknown. And we're practically done. We got the grams. There it is, 5.9864 grams of the unknown. We have the moles of the unknown, so we just merely have to divide them out. And so we say 5.9864 grams unknown divided by the moles unknown, which we just calculated. That's the moles unknown, and we put this in our calculator, and we get a final answer, 981.7 grams per mole, unknown acid. And there is the molecular weight of our unknown, determined by titration.